So I'm going to talk about gauge origami. I apologize, this title is probably would be more appropriate for Okinawa conference than for Beijing conference, but that's life. So I'll start by reminding some of the notions I spoke about 2 years ago, the strings at Princeton. A lot of things has changed since then. For example, Douglas at that time meant Mike, and Stanford was just the university. And so I assume some of you have forgotten the non-perturbative Dyson-Schwinger equations and novel symmetries of quantum field theory. So let's start with the ordinary Dyson-Schwinger equations, which follow from the invariance of path integral under their small deformations of the contour or small changes of variables under the sign of the integral, which lead to the quantum equations of motion, where the insertion of the classical equations of motion viewed as an operator in some correlation function can be expressed as the correlation function of fewer operators. And so if you're lucky, if you chose nice observables and perhaps in some limit, these equations can close and so can form a system of equations you can study. For example, in gauge theory, let's say in large N gauge theory, the Wilson loop observables, normalized Wilson loop observables in the fundamental representation, in the 't Hooft limit, form a system of equation which looks like a closed system of equation in the loop space, some kind of Laplacian applied to this Wilson loop is equal to the distributional loop space supported on the loops which split into two loops where you have a product of such operators. And in the toy model of gauge theory, the matrix model, just matrix integral, more familiar, better studied case because here it's essentially solvable. Instead of the Wilson loop, you use the resolvent of the matrix, trace of 1 over x minus phi. Phi is the matrix you are integrating over, and x is just an auxiliary variable. So this observable as a function of the auxiliary variable x has singularities, has poles at the positions of the eigenvalues of the matrix. But if you take the sum of the expectation value of this observable and the derivative of the potential and take a square, then the Dyson-Schwinger equations of the matrix model, also known as loop equations, state that the square of this function is actually a polynomial in x, has no singularities. So in more realistic quantum field theories, in addition to the integration, we also have summation over various topological sectors, over instanton sectors, for example, in gauge theory. And so I would like to study the generalization of the Dyson-Schwinger equations, which would follow from the sort of large deformations of the path integral contour, where you would shift the contour of integration of gauge fields with instantons in the instanton sector n by sort of a small, almost everywhere small deformation, which will nevertheless take you into the sector of a different topology. So you would like graft into your given gauge field configuration almost a point, small size instanton, and so you will land in a different instanton sector. And hopefully, by comparing the path integrals on these two sectors, you can derive new identities between correlation functions. So this sounds vague and almost impossible because, after all, changing the topology is not a small thing. So why would the path integral measure be comparable in different instanton sectors? Nevertheless, the experience shows that it is possible to compare, and the explicit realization of this idea was found in the context of n equals 2 supersymmetric 4-dimensional gauge theories and 2-dimensional signal models, and also in higher dimensions with the same supersymmetry, same amount of supersymmetry. So we'll start with the choice of observables for these equations, for this generalization of Dirichlet-Schmidt equations. So in four-dimensional n equals 2 gauge theory, there is a scalar phi in the vector multiplet. So it's a complex field in adjoint representation. And the naive observable, which is sort of analogous to the resolvent in the matrix model case, would be the characteristic polynomial. So the product of x minus the eigenvalues of this matrix phi, where x is again an auxiliary variable. So this is a naive definition. More precisely, you define this observable as a exponential of this generating function of all single trace operators. And so if phi were phi is a fine-dimensional n by n matrix, then the products of these traces would obey certain identities which would guarantee that this exponential of this infinite sum will actually be a polynomial. But in fact, it turns out that because of the mixing of this field phi with gluinos, and because of the fact that in incidental backgrounds gluinos have zero modes, these algebraic identities, algebraic relations between traces receive corrections. And so this sum doesn't sum up exactly to a polynomial. In fact, this expression requires poles in the variable x. And the larger the number, the more poles it has. And analogously, if you have several gauge factors, several UN factors, then you will define several such observables, and they will all get poles in the incidental backgrounds. And surprisingly, the claim is that for at least for quiver gauge theories, there exists a way to correct this observable y by adding extra terms, also given in terms of y, with arguments shifted by linear combinations of masses of fields in the bifundamental representations, and with coefficients which depend on the masses of fundamental hypermultiplets and of gauge couplings, such that the expectation value of this corrected y observable is actually a polynomial in x. So all poles will cancel. And as I said, these coefficients depend on gauge couplings. So in fact, these corrections, they sort of account they come from the contributions. So if you look at this expectation value and try to see how come the poles got cancelled, they get cancelled by the contributions of different incidental sectors. So the pole in incidental sector n is cancelled by another pole which comes from incidental sector n plus 1, and so on and so forth. So such expressions which start with y and then are corrected, we call the fundamental gauge characters, for the reasons which will be clear later. And so these fundamental gauge characters are the four-dimensional analogs of the matrix models expression, where you took the square of this function. So the fact that you take a square has to do with certain Weyl symmetry, just like the characters have to do with the Weyl symmetry. And so these are not the all such possible expressions. You can actually form more complicated expressions where you take the products of these things and also correct them. And they all have the main feature is that the expectation values have no poles as the functions of the auxiliary variable x. Now, this claim that there are no poles, you can translate this into the Zabry-Putin geometry of the low energy effective theory. And if the theory is subject to the so-called omega deformation, then these characters become, these expressions, they also get deformed by the parameters of omega deformations. And then these gauge characters are called the QQ characters in this case. So the simplest example of such a correction term, such an expression, in the SUN gauge theory with 2n fundamental hypermultiplets. So I know that Nachi is here, so I'm not calling this UN gauge theory. This simplest fundamental character, QQ character, is a sum of two terms. So first you have this Y expression whose argument is shifted by some parameters of omega deformation. And so that will have poles in each instanton sector. And then there is a term which carries exactly 1 unit of instanton amplitude and product of all fundamental masses. So you have 2n such terms. And then 1 over y. And so this expression will have zeros in the instanton sectors with one lower instanton charge, and this they will cancel these poles. So this is where the introduction stops. Now the main topic of this talk is to explain the origin of these expressions. So where do these? So originally they were obtained by brute force, but it turns out that there is a systematic procedure for getting them, for obtaining them. So in fact, these QQ characters and the gauge characters are partition functions of a point-like defect in gauge theory. So it's a local operator which is a partition function of a defect which sits at a point in space-time, and this defect can be engineering using intersecting branes. So imagine we are living in the brane world scenario where the standard model is confined to some brane or a stack of branes, and gravity propagates in the bulk. And it could be that in addition to the stack of branes on which our theory lives, so which we can call a physical stack of branes, there could be other branes in floating around. And these other branes could intersect our stack of branes or could be nearby. And these intersections would exhibit themselves as defects in our world volume, or it could be, so these defects could be of point-like nature, or they could be spread over surfaces or lines, and so on and so forth. So, for example, we imagine having 3 stacks of branes, each stack of branes spanning 4-dimensional space. Some of these spaces will be Euclidean. And so the observer who lives on one of these stacks of branes, let's say brane 1, 2, will observe 2 defects, 2 surface defects which intersect at the point, and the point-like defect. And you can actually preserve you can preserve 0-2 supersymmetry in 2 dimensions by combining up to 6 stacks of d5 branes and anti-d5s, which will intersect along a 2-dimensional Minkowski space, and then share various degrees of intersections along the 2-dimensional or 0-dimensional times R11 subspaces. So this picture is kind of difficult to read. I tried to squeeze all 6 4-dimensional spaces onto the 2-dimensional slide, which is impossible. But there are better pictures which I will present immediately. So we just should remember that for each stack of branes spanning its own 4-dimensional space, or 4-dimensional or 6-dimensional, there is a Chan-Paton space, which I will call NAB. And so A and B are a pair of indices, each chosen from 1 to 4. And so this is where each C2 AB will span some gauge theory locally, some UN NAB gauge theory, but these theories will talk to each other via defects which they share. So the better picture to try to fit all possibilities onto a plane is to represent each complex line by an axis, and then if there is a stack of branes which spans 2 of these 2 complex dimensions, I will put a little blob at the corner. So here is the picture for the usual 4-dimensional n equals 4 theory, which lives in the space C2 with coordinates 1, 2, and it's a UN 1, 2 gauge theory. And now we add another theory. Now we add another UN theory, which will live in a space C2 with coordinates 2 and 3, and these two theories share one complex line. So these two n equals 4 theories will interact through some two-dimensional defect theory. And you can continue, so add one more theory, and 4, and 5, and 6. Oops, that's too much. It's a very sensitive thing. Okay. Right. So this picture, which I start with 3 stacks of brains intersecting in C3, will correspond to this picture in this way. So the idea is now, suppose somehow you manage to integrate out all degrees of freedom on all stacks of brains except for one. Then you will generate some interaction in your original theory or in physical theory, which will be either localized at a point or spread as a surface defect. Okay, and so one integrates degrees of freedom using supersymmetry and localization. These stacks were chosen carefully so as to preserve some fraction of supersymmetry, and so one could use exact supersymmetric computations to evaluate these integrals. And so one feature of this integration is that you can represent the degrees of freedom which are associated to instantons. So the instantons are actually shared by all the stacks of brains, and the instantons are free to travel from one stack to another, and that's actually the explanation why such transitions, which seem quite unnatural from the point of view of the gauge theory on a single copy of four-dimensional space-time, why they become possible when you take this whole picture into consideration. So what seems to be two different instanton sectors to our observer living in our space are actually belong to the same instanton sector in the theory with two stacks of brains, where just one instanton went to another stack. And so there's a mathematical description of this set of space of such instantons, which involves certain matrices which generalize ADHM constructions. So on each two-dimensional plane, you will have the data of the usual ADHM construction of instantons in 4 dimensions, with 2 square matrices and 2 rectangular matrices. But altogether, you have 4 square complex matrices and 6 pairs of rectangular matrices. And they solve interesting equations, which I will write very briefly. So in the ordinary 4-dimensional gauge theory, in describing instantons of UN gauge group, you set this combination of quadratic matrices and rectangular matrices to 0. And in this story, where you have up to 6 stacks of brains, you impose 7 equations in total for 8 Hermitian square matrices, which together with the UK symmetry action precisely eliminate all these degrees of freedom in quadratic matrices. And then there are additional equations which are not familiar in the usual ADHM construction, which tell you that the B matrices of one set of brains should basically annihilate the I and J matrices from another set of brains. And then there are some cross equations which come from integrating out the open strings which connect higher dimensional brains. So with all these equations, you get some modular space over which you integrate, and that produces a partition function which becomes a kind of statistical mechanical model, which is of interest of its own. And the partition function of the statistical mechanical model is the partition function of what I call the gauge origami, which is also the partition function of this union of gauge theories. And the main claim is that as a function of Coulomb parameters, which physically are the separations of these stacks of brains in the remaining transverse 2 dimensions, this partition function has no singularities. And and the fact that the partition function has no singularities, by expanding it in the powers of these Coulomb parameters and setting to 0 the coefficients in all negative powers, you get a bunch of identities, which are the non-perturbative Dyson-Schwinger equations. And as an application, you can derive all known statements of the BPS CFT correspondence that, for the A-type quiver gauge theories, with or without defects, the partition functions obey the BPZ or KZ type equations of conformal blocks of two-dimensional conformal field theories. And now with this, with the presence of these stacks of branes which intersect along two-dimensional surfaces, also superconformal field theories. So you can realize not only Cosmoody algebras, let's say, but also super Cosmoodies. And I'm sure there are more applications to follow. Thank you for your attention.
Any questions?
Do you see any connection with topological strings and these defects?
Not directly, but I think so each of these theories individually, without other branes, these are n equals 2 star gauge theories. What I forgot to mention, maybe I mentioned on some slides, there are also, you can also do orbifolds, so you can generate all possible quiver theories we know of by these constructions. And so these theories, of course, can be geometrically engineered by topological strings on local Calabi-Yaus. But now combining these theories so that they intersect along different surfaces or points sounds like an exciting possibility of doing something with topological strings, where you have a study topological string on a singular Calabi-Yau, or maybe not even Calabi-Yau, the singular space, which is Calabi-Yau as a whole, but the local pieces are, for example, Fano varieties, so that you have the top degree form has poles, but these poles have opposite residues, so different components. So we normally don't study topological strings on such manifolds, but this picture suggests that we should. And another slight abstraction to doing this in a strictly speaking topological string is that here, to make things interesting, are usually, so there are 4 omega deformation parameters here, which sum up to 0. And if you insist that 2 of them sum to 0, things become kind of rather singular. So it should be the refined topological string. I don't really understand what it is. So.